Good morning, all of you. Let us discuss a new topic, that is viscosity. So, we have studied about friction in laws of motion, friction between objects when they move, that we have seen in laws of motion. So, friction is not only applicable for solids, it's applicable even for fluids. So, the production of force of friction is seen in liquid as well as in gas. But comparatively, gases, this friction is very low, negligibly small. So let's concentrate on friction created in a liquid. This friction created in a liquid is called a viscosity. So all the fluids produces friction, and the friction here is termed as viscosity. So let's consider a liquid in motion. So when the liquid is in motion, there is a friction acting between different layers of the fluid, and also there is a friction between liquid and the container or the tube through which it is flowing. So this force of friction is called viscous force, or it's even known as viscous drag. This phenomenon is actually known as viscosity. So almost all liquids are viscous in nature. Depending on the density, the viscous force is different for different liquids. So connected to this viscosity, there is a law suggested by Newton. So for example, let's consider a fluid which is steadily flowing with parallel layers. So let's consider any two layers of area capital A. Let the two layers be P and Q. Here is one layer of liquid, another layer of liquid. Both are moving towards the right side. This is the bottom part of the liquid which is in contact with the surface. Then this layer P, is at a distance x from the bottom part, and this next layer Q is at a distance, little more distance, x plus dx, little extra distance is there, where dx is the separation between the two layers we have considered, and these two are moving at different speed. Let this layer move with a speed v, and this layer move with a speed v plus dv. And after so many observations, Newton understood that the layer which is in contact with a solid surface, for example, if it is a tube, the liquid layer in contact with the sides of the tube, there all friction will be more, so the liquid speed will be lesser. But at the region where this liquid is only in contact with another layer of the liquid, there speed will be comparatively more. So if this is the contact surface, if this layer moves with a speed v, this layer moves with a greater speed, that is v plus a dv, because this layer will feel more friction with the surface also. So after the study done by Newton, he understood certain phenomena, certain factors. One is the frictional force, that is the viscous force, directly proportional to area of the layers in contact, and that is directly proportional to the velocity gradient. Velocity gradient means the change in velocity by the separation, which can also be called as the rate of change of velocity with respect to distance. This is actually the change in velocity. This is d is change in velocity by the small distance, dv by dx. So considering the two factors, he wrote like this: f is directly proportional to dv by dx, f is proportional to a also, so he wrote together f is proportional to a dv by dx, f is proportional to a dv by dx. And here Newton introduced one constant. That constant is called coefficient of viscosity, and that letter is eta. So here he made an equation f is equal to minus eta a dv by dx. This minus sign shows that the viscous force is acting in the opposite direction of movement of the fluid. We all know friction always try to be in the opposite direction of motion in most of the situations. So here also, in the case of liquid also, this friction is trying to oppose the relative motion of different layers of the liquid. So hence this negative sign is given. So let's consider a little more about the coefficient of viscosity. If we neglect the negative sign, which gives only the direction, we can write f is equal to eta a dv by dx. If we consider area is 1, that means unit area of area of the layer if you consider, and the velocity gradient, that is dv by dx, that's also if we consider as 1, we get f is equal to eta. Hence coefficient of viscosity can be defined as the viscous force. This viscous force will be acting tangentially to the layer. So it can be defined as tangential viscous force required to maintain unit velocity gradient, that is dv by dx, between two layers of a liquid of unit area of contact. So the area of contact of the layers if you consider as unity, and the velocity gradient also if we consider as unity, f will be equal to eta. And the unit of this coefficient of viscosity is known as Poiseuille. And that will be equal to kilogram per meter per second, or a Newton second meter raised to minus 2. This equation we can check, this unit you can check using the equation f is equal to eta a dv by dx, or eta is equal to f dx by a dv. And this 1 Newton per meter square second, or 1 kilogram per meter second, this is known as Poiseuille. If we check the dimensional formula, it will come to ml to the power minus 1 t to the power minus 1. So that's about viscosity and coefficient of viscosity. Also Poiseuille is a scientist, we all know. He has suggested one equation, one formula for volume of liquid flowing out per second through a pipe. So the volume of liquid per second, that is V by T. Volume is V, time is T. So V by T if you take, we get volume per unit time. That can be represented as Q. A letter can be given for this. Volume of liquid per time, that is the rate of flow of volume. He told that it will be equal to pi P, where P is the pressure difference between the ends of the tube. So you consider a tube, the volume of liquid flowing in 1 second, that is what this equation says, that is pi p r to the power 4 by 8 eta L, where the tube's length is L, its radius is r, and eta is the coefficient of viscosity of the liquid in which it's flowing, and P is the pressure difference between ends of the tube. No derivation, it's actually an assumption based equation. So the assumptions made for getting these equations are: the flow of liquid is steady and parallel to the axis of the tube. It should be a streamline or a steady flow. There is no much pressure variation inside the tube, another condition. And at the walls of the tube, the velocity of the liquid is 0. And at the center part, at the axis, speed is maximum. And the tube should be held straight, should be horizontal. If these conditions are satisfied, he said the volume of the liquid flowing is pi p r raised to 4 by 8 eta L. So this is an assumption based equation, but it's holding good. So let's consider this equation also. So no need of any derivation or anything. Consider the equation directly. Another one idea, similarly, a law is there, that is Stokes law. As per Stokes law, if you put a very small object, a spherical object, inside a fluid, suppose you drop a small spherical object inside a fluid, it will move down due to gravity. But after some time, because of the viscous nature of the fluid, it will move with a uniform velocity. It will come down with a uniform velocity. So for example, if you take a very long tube, fill it with a particular liquid, you drop a small spherical object inside, that object will come down with a particular speed. A uniform velocity it takes. If v is that a uniform velocity and a is the radius of the tube or the radius of the pipe through which the object is dropped, then there is a viscous force, and that force is given by 6 pi eta av. This is also an empirical formula, you need not study the derivation or anything, it will be useful for some other purpose. So the force acting on the spherical body dropped in a fluid of viscosity eta is given by 6 pi eta av. So using this, let us consider a small derivation part, that is for a body dropped inside a fluid. Suppose you take a container, in that there can be a fluid. If you drop a small spherical object inside, it falls down through the liquid. It, after some time, while it is in motion, it attains a constant velocity, and that velocity is called terminal velocity. Because of the fluid, friction, gravity, everything, considering all the force, when all the forces are particularly balanced, this fluid, this object comes through the fluid with a particular velocity. That velocity is called terminal velocity. So let us make an equation for that also using this Stokes law. So let us consider a container in which a liquid of density rho is taken. A small object of spherical shape of radius a is dropped inside it. So this is the setup. There is a container in which a liquid is taken. This liquid density is rho, and you take a ball, a spherical ball of radius a, having volume v, that is 4 by 3 pi a cube. 4 by 3 pi a cube. So the parameters involved here are, one is the radius, that is a, volume is 4 by 3 pi a cube, and this liquid density is rho we told, but this object density, let it be another quantity, that is sigma. So density of the sphere is, spherical object is sigma. Now when this body is coming down, there are some forces acting on it. One is the weight of this body acting downward, that is a W, weight of the body acting downward. Now we already studied in 9th standard that there is a upthrust acting on the body. Whenever a body is in a fluid, there is an upthrust acting. That upthrust was given by V rho g. if V is the volume of the body, rho is the density of the fluid, and G is the acceleration due to gravity, the upthrust U is given by V rho G. Here V is the volume of the object, rho is the density of the density of the fluid. And one more thing, this weight of this body W can be written as mg, where m is the mass of this object. Mass can be written as volume into density, so V into density of the object sigma into g. This is the weight of the body. So two forces we discussed. One is the weight of the body, V sigma g, and upthrust V rho g. Just now we studied one more force, that is the viscous force. That viscous force was, if I mark it as F, that is viscous force is 6 pi eta AV, where eta is the coefficient of viscosity of this liquid, A is the radius of this body, V is the terminal velocity. Terminal velocity means after this ball comes down, when all the forces are balanced, this body comes down with a particular velocity. That velocity is called terminal velocity. So 6 pi eta AV is the viscous force, that is the frictional force. So let us check the direction. Weight is acting downward, body moves downward, that's why velocity direction is downward. Upthrust is acting upward. Friction try to oppose the movement of the ball, that is also acting upward. So two upward force and one downward force. At a particular situation, when all the three are balanced, the body comes down with the net force acting on it will be balanced. So the body comes down will be with the speed V, a constant velocity V. That is, two upward force and the downward force are equal. One more idea which we have studied in 9th standard is, the actual weight of the body is W, but there is an upthrust acting U, which means there is an apparent weight, that is an apparent weight, I can mark it as WA, which is the original weight minus the upthrust, which you studied in 9th standard. So this apparent weight, that is W minus U, when it is equal to the viscous force F, this body's net force is 0, the body is balanced. So as I say, these two, W minus U is the apparent weight of the body, that is balanced by the viscous force. Then after that the body comes down with a steady velocity. So let us first find the apparent weight, that is W minus U. W we know, we have just now got V sigma g and U V rho g. If you substitute all this, you get an equation V into sigma minus rho into g. Volume is 4 by 3 pi a cube, that also we can substitute here. And just now we told this apparent weight, when it is balanced by the frictional force, that is a viscous force, the body comes down with a constant terminal velocity. So this WA, we write it as 4 by 3 pi a cube sigma minus rho g, and this viscous force is 6 pi eta a V. V here we substitute Vt, we write as Vt, showing that terminal velocity it is. So if you cancel out all those things and rearrange, we get this terminal velocity as, let it be V small letter v, terminal velocity as 2 by 9 eta a square sigma minus rho into g. So terminal velocity depends on radius of this body, density of the body, density of the fluid, and the terminal velocity, the viscous coefficient of viscosity of the liquid. So all those things are dependent. So as per this equation, the terminal velocity of a bigger object will be greater, because it depends on directly on the radius, As the radius is greater, terminal velocity will be greater. Suppose a special case, suppose this sigma and rho are equal. The terminal velocity will be 0, which means the body will be staying inside the fluid at a particular height. If the liquid is of more viscosity, then terminal velocity will be slow, very low. They are inversely proportional. Yes, eta is more, viscosity is more, velocity will be lesser. So if you analyze different liquids, for example, water, if you take mercury, different liquids will have different viscosity. You take honey, we know honey is thicker than water, so its viscous nature will be more. This will be more viscous. So this terminal velocity and viscous nature are connected.